Imagine a day that's almost exactly like Earth's, but a year that stretches for nearly 2 of ours. Now, picture a world where it never ever rains, yet there's ice hidden, well, pretty much everywhere. We're talking about Mars, our mysterious red neighbor, a planet that holds, secrets about our own solar system's past and perhaps our future. Welcome to another episode of Tiny Talks Big Ideas podcast. Today we're taking a deep dive into the red planet. We're pulling insights from a fantastic collection of sources, fact sheets from the Smithsonian's National Museum of Natural History and National Air and Space Museum, and also some pretty advanced academic texts on Martian geology and planetary science. Our mission, to cut through the vast amount of information out there and really pull out the most compelling insights, the surprising facts, and the crucial takeaways about Mars. We want to leave you truly well-informed. Okay, let's unpack this.
Yeah, it's an incredible journey to take. Mars has always fascinated us, hasn't it? And with every new mission, it feels like we peel back another layer, revealing a world that's, much more dynamic and complex than we maybe first thought.
Absolutely. So for you, our listener, let's start with the real basics. How does a Martian day compare to ours? And what about its year? Is it dramatically different?
You might actually be surprised by the Martian day. It spins on its axis in 24 hours and 38 minutes. That's remarkably close to an Earth day.
Wow, okay.
So a Mars day or a Sol would feel quite familiar, if you were standing on the surface. The year, though, that's a different story. It's significantly longer.
Right.
Mars takes 687 Earth days to go around the sun once. So that's almost 2 of our years.
Almost 2 years. That's quite a stretch. And its distance from us and from the sun, does that stay the same, or is Mars kind of a moving target?
Oh, it's definitely a moving target. Its distance from Earth changes, dramatically because both planets are orbiting the sun at different speeds on different paths.
Makes sense.
At its closest, Mars can be just 34 million miles away, which sounds like a lot, but it's only about 1/3 of Earth's average distance from the sun.
Relatively close, then, in space terms.
Exactly. But it can also swing much, much farther away, over 200 million miles. That's why, its brightness changes so much in our night sky. On average, though, Mars orbits the sun at about 141 million miles, so it's roughly 1.5 times further out than we are.
Okay, that explains why the red planet isn't always equally bright. And speaking of that iconic red color, why is Mars red? And what about water? Does it rain there, or is it really the dry desert we often imagine?
Well, that striking red color, its most famous feature perhaps, it comes down to something really common. Rust.
Rust?
Yeah, basically. The rocks and the dust on Mars are super rich in iron. And over billions of years, this iron has reacted with what little atmosphere there is, forming iron oxides. Essentially rust, just like you'd see on old metal here on Earth. And that fine rusty dust covers almost everything, giving Mars its distinctive color. Now, about water, no, it definitely doesn't rain on Mars like we know it. The atmospheric pressure is just way too low, and it's too cold for liquid water to be stable on the surface for long. But, and this is a key point, while there's no liquid water cycle like ours, there is a lot of ice.
Ice, right. You mentioned that.
Yeah, carbon dioxide from the thin atmosphere freezes out at the poles in winter, kind of like our dry ice snows on Earth poles. But even more importantly, we found huge amounts of actual water ice. It's trapped in rocks, buried under the surface, hiding in shaded craters, especially towards the poles.
That's fascinating. A world that never rains but is full of hidden ice. And those darker patches we see sometimes, they aren't just shadows, are they?
No, exactly. Those are areas where the wind has basically scoured away the top layer of that reddish dust, exposing the darker volcanic rock underneath.
So it's about how light reflects off it.
Precisely. Less light bounces off that darker rock, so it looks like dark patches from orbit. It's like seeing the bedrock beneath the soil.
So how do we know all this stuff? From the day length being so similar to finding hidden ice? I mean, our understanding of Mars has been completely changed by spacecraft, right?
Yeah.
This is where it gets really interesting.
It really is.
Yeah.
It's a huge testament to human ingenuity and, frankly, persistence. Think about this. Out of 46 spacecraft missions specifically sent to study Mars, almost half of them failed.
Wow, nearly half. That's tough.
It is. Mars is hard. But here's the amazing part. 28 missions have successfully reached Mars and sent back just incredible amounts of data. And right now, as you speak, there are 11 spacecraft actively working there.
11? That's quite a fleet.
It is. There are 8 orbiters circling the planet, 2 rovers driving on the surface, and 1 stationary lander. And what's really inspiring, I think, is that it's a truly international effort now.
Ah, yeah.
We've got orbiters from the European Space Agency, from China, India, the United Arab Emirates, all working alongside the U.S. missions. China's Tianwen-1 mission, for instance, successfully put both an orbiter and a rover on Mars in 2021, a major achievement.
That's fantastic.
Yep.
It all builds on those early, pioneering missions like Mariner 9, which first showed us those mysterious channels hinting at past water.
Exactly. Game changer, Mariner 9.
And then Viking, giving us our first actual pictures from the surface, those amazing color views of that rocky, dusty ground. They really started shifting our view from Mars being just a dead rock to, well, something with a history. So with all these robots sending data back, what is Mars actually made of? Is it basically like Earth inside, or is it something totally different?
Well, at its heart, Mars is a rocky planet, much like Earth, and we find many of the same kinds of minerals there. Basaltic rock, volcanic rock, very common.
Right.
Remote sensing tells us the crust is largely iron-rich volcanic material. But what's really cool is how the rocks themselves tell a story. Scientists found minerals like crystalline gray hematite.
Hematite.
Yeah, a form of iron oxide. But finding it in that crystalline form strongly suggests it formed in the presence of iron-rich water, liquid water, interacting with the rocks.
Water again, so
Yeah.
physical evidence in the minerals.
Exactly, a big clue about its past. And we even have actual pieces of Mars here on Earth. Martian meteorites.
You mean rocks that got blasted off Mars and landed here?
That's right. We call them SNCs after the first few finds. They're volcanic rocks ejected by big impacts on Mars. And what's really wild is that most of them are surprisingly young, geologically speaking. Less than 1.35 billion years old.
So volcanoes were active on Mars much more recently than we used to think.
Absolutely. Confirms recent, or relatively recent, volcanism.
That's mind-blowing. Literal pieces of Mars. Okay, so what does all this tell us about what's going on inside the planet? What about its magnetic field? I remember hearing Mars lost its magnetic field.
Yeah, connecting the surface geology to the interior is key. Models suggest Mars formed really hot and really fast, maybe within the first 5 million years of the solar system.
Wow, quick start.
Very quick. Led to a magma ocean, differentiation-heavy stuff sinking to the core, lighter stuff forming the crust, all probably done within about 20 million years. That initial heat was immense.
And the magnetic field.
Right. The magnetic field story is fascinating. Data from the Mars Global Surveyor, MGS, found something amazing. Patches of magnetized rock in the oldest parts of the crust.
Magnetized rock.
Yeah, remnant magnetism. And it forms these lineated patterns, stripes of alternating magnetic polarity. Really similar to what we see on Earth's ocean floors related to seafloor spreading.
So that implies.
It strongly implies Mars used to have an active magnetic dynamo in its core, just like Earth does now, generating a global magnetic field, a protective shield.
But it doesn't have one now. So what happened?
That's the big question. The fact that the global field is gone means its core isn't generating one anymore. Either it's not convecting vigorously enough, not churning like Earth's outer core, or maybe it's not solidifying in the right way. The loss of that shield, probably around 4 billion years ago, was a huge turning point for Mars.
So a planet that basically lost its protective shield early on. What do we think the inside looks like now, the structure?
We infer it's differentiated, like Earth. A crust, a mantle, and a core. The crust seems quite thick, maybe averaging 100 kilometers, but thicker in the southern highlands. Then a really thick mantle, maybe 1,700 to 2,100 kilometers thick. And then the core.
And the core itself. Solid. Liquid.
Still one of the big unknowns, actually. Its radius is estimated between 1,300 and 1,700 kilometers, but whether it's mostly liquid, mostly solid, or some mix, that's something current and future missions are trying to pin down. Knowing that would tell us so much about how Mars cooled down.
That's a huge amount of detail about stuff we can't, directly see or drill into yet. How do we get that information? How do we peer beneath the surface from orbit?
Great question. We use really sophisticated radar instruments on the orbiters. MOLA, the Mars Orbiter Laser Altimeter, wasn't radar, but used lasers to map topography and surface roughness incredibly precisely. It showed the southern highlands are much rougher, mostly due to all the impact craters, while the northern plains are smoother, probably covered by younger sediments or lava flows. There's even this strange area called the Stealth region.
Stealth.
Yeah, in the Medusae Fossae Formation, it barely reflects any radar signals at all. The thinking is it must be covered by really thick layers of super fine-grained material, maybe volcanic ash or dust, that just absorbs the radar waves.
Weird.
It is. But for actually seeing under the surface, we use ground-penetrating radar. Instruments like MARSIS on Mars Express and SHARAD on the Mars Reconnaissance Orbiter, they send radar pulses down and listen for the echoes bouncing off different layers underground.
Like sonar, but with radar.
Exactly. And they've been incredibly successful at mapping out buried ice deposits, especially in the polar caps, and seeing variations in rock layers beneath the dust, giving us a kind of 3D picture of the shallow subsurface.
Okay, so we've looked inside Mars, peered beneath its skin. Let's talk about what's right there on the surface. Mars is famously scarred by impacts.
Yeah.
But these craters aren't just random holes, are they? They tell a story.
Oh, absolutely. Craters are fundamental to understanding Mars. They're like geological clocks. We see simple, bowl-shaped ones, and then much larger, complex craters with features like central peaks, terraced walls, even rings inside.
And they tell us about age.
Yes, primarily. The density of craters, how many craters are packed into a certain area, is our main tool for figuring out the relative age of surfaces. More craters means an older surface. The oldest terrains are absolutely saturated with craters, remnants from the solar system's chaotic early days, that period we call the late heavy bombardment.
Right, when everything was getting hit.
Pretty much. But Mars isn't just about getting hit. It's also been incredibly active volcanically. It's a volcanic titan, really.
And home to some truly enormous volcanoes.
Right.
Bigger than anything on Earth.
By far. The Tharsis region is dominated by these huge shield volcanoes. Olympus Mons is the champion, the largest known volcano in the entire solar system. Its base is so wide it would cover Arizona.
That's just staggering.
It is. And there are others nearby like Arja Mons, Pavonis Mons, Escreas Mons, plus vast plains formed by ancient floods of lava, flood basalts. Volcanism has been a major player on Mars.
Mars also shows signs of huge geological forces stretching and squeezing, doesn't it? Not just impacts or volcanoes.
That's right. You see evidence of massive tectonic stresses. The most dramatic example is Valles Marineris.
The giant canyon system.
Exactly. It's not just one canyon. It's this interconnected system stretching 4,000 kilometers east-west. That's like the width of the continental U.S. And it's incredibly deep, up to 6 kilometers in places.
What formed that?
It's primarily an extensional feature. The crust was pulled apart, likely related to the uplift of the nearby Tharsis volcanic region. It's ripped open the crust, exposing these amazing layers of rock that tell us about billions of years of Martian history. And it's full of massive landslides, too.
Wow. And squeezing. Signs of compression?
Yeah, we see those too. Features called wrinkle ridges. They look like crumpled fabric on the surface, and they form when the crust is compressed or squeezed. You see them a lot on those extensive lava plains.
So, impacts, volcanoes, massive stretching, squeezing. But it also seems like wind, water, and ice have been huge sculptors too, even if the water isn't obvious now.
Definitely. They've all left their mark, profoundly shaping the landscape we see today. Wind action, what we call aeolian processes, is huge on Mars.
Like the dust storms.
Yes, but also shaping the land itself. We see all sorts of sand dunes, crescent-shaped barchans, long transverse dunes, linear ones. Wind also creates bright streaks where dust is deposited and dark streaks where it's scoured away. And these amazing, elongated, streamlined hills carved from bedrock by wind erosion called yardangs. Wind is a powerful force there.
And water, despite it being so dry now.
The evidence for past water is overwhelming. We see these branching valley networks, especially on the older terrains, that look just like river systems on Earth, suggest rainfall or groundwater flow long ago.
River Valley.
And then there are enormous outflow channels, much bigger, that look like they were carved by catastrophic floods, maybe from groundwater bursting out or lakes overflowing. We even see features inside craters that look like ancient lake beds, with shorelines and deltas where rivers flowed in, like in Eberswald or Holden craters, and smaller gullies on steep slopes that might indicate more recent brief flows.
So the water evidence is really diverse. And the ice, not just the poles.
No, ice is critical. The polar caps, north and south, are these huge layered deposits of water ice mixed with dust, capped by seasonal CO2 frost. The North Pole has these amazing spiral troughs winding outwards. The south has scarps, both probably shaped by sublimation and wind. But away from the poles, especially at high latitudes, we see ground that looks like permafrost on Earth. weird polygonal patterns from freeze-thaw cycles, small mounds that could be ice-cored hills called pingos, depressions from ground ice melting, and even closer to the equator on slopes you find these things called lobate debris aprons, basically flowing mixtures of rock and ice like slow glaciers, remnants of past ice ages maybe. Mars has a hidden icy past and present.
Okay, so knowing all that history, what's Mars's atmosphere actually like today? How does it affect things on the surface now?
Today, Mars has a very, very thin atmosphere. It's about 1% the pressure of Earth's at sea level, and it's almost entirely carbon dioxide, about 95%.
95% CO2.
Wow. Yeah, and it has this really strong seasonal cycle driven by that CO2. In winter, a huge amount of the atmosphere, maybe up to 20 or 30%, actually freezes out onto the polar cap. Then in summer, it turns back into gas sublimits. This causes a massive global swing in surface pressure throughout the year, something we just don't see on Earth.
A 20% pressure change. That's wild.
It is. There's a little bit of water vapor, nitrogen, argon too, but it's overwhelmingly CO2. Circulation is driven by solar heating and the planet's rotation, like Earth, but it's a much simpler, thinner system, not much protection.
But as we've said, there's so much evidence Mars was once wetter, warmer maybe. That implies a thicker atmosphere, right? So what happened to it? This seems like a huge puzzle.
It really is one of the biggest Martian mysteries, and tied into it is the faint young sun paradox.
Right, the sun was weaker back then.
Exactly. About 4 billion years ago, when we see all that evidence for liquid water, the sun was maybe 25 to 30% less luminous than today. So how was Mars warm enough for liquid water? A thick CO2 atmosphere could have provided greenhouse warming, but models suggest even several bars of CO2 might not have been enough or it would condense out.
So it's tricky to explain the warmth, but what about losing the atmosphere?
That part seems clear, linked to losing the magnetic field. Once that shield was down, around 4 billion years ago, the solar wind, that constant stream of charged particles from the sun, could directly hit the upper atmosphere.
And just strip it away.
Pretty much. Through processes like sputtering, where high-energy particles knock atmospheric atoms and molecules out into space, and other collision processes, over billions of years, this could have removed a huge amount of Mars's early, thicker atmosphere, leaving the thin one we see today.
Okay, so connecting this all together, where did Mars's water originally come from? Was it just part of the planet's formation? And how much do we think there actually was?
Current thinking is that a lot of Mars's water, maybe most of it, was delivered by impacts, asteroids, and comets hitting the planet early in its history, rather than just being baked in during formation.
Impacts bringing water.
Yeah. And we have evidence for massive water loss tied to the atmospheric loss. The ratio of deuterium, that's heavy hydrogen, to normal hydrogen in the Martian atmosphere is much higher than on Earth, meaning the lighter hydrogen escaped to space more easily over time, leaving behind a higher concentration of the heavier deuterium. It's a fingerprint of significant water loss. As for how much? Well, models based on geology and that DH ratio suggest Mars could have once had enough water to form a global ocean covering the entire planet, maybe hundreds, even thousands of meters deep.
A global ocean. That's incredible to imagine. So how do scientists track this water story through the rocks if the ocean itself is gone?
The minerals tell the tale. The Omega instrument on Mars Express, a spectrometer, mapped out mineral distributions and found a really interesting sequence, almost like geological eras defined by water chemistry.
Eras of water.
Kind of. First, the Phyllosian period. The earliest time, early to middle Noatian in geological terms. This is when phyllosilicates, clay minerals, formed widely. Clays need abundant, relatively neutral water to form, so a wetter, maybe more habitable early Mars.
Okay, the clay era. What came next?
Then came the Fijian period, late Noachian, early Hesperian. Volcanism seems to have ramped up, releasing lots of sulfur into the atmosphere and water. This sulfur reacted with the water to form sulfate minerals. Conditions likely became much more acidic.
So wet neutral, then wet and acidic.
Exactly. And finally, the Siderichian period, late Hesperian through the present Amazonian. During this long era, and hydrospheric oxides, basically rust became the dominant signature. Liquid water seems to have become rare, maybe only appearing locally and briefly. It's a story of drying out and changing chemistry.
What a dramatic transformation. From clays to sulfates to rust.
It really paints a picture of environmental change. But remember, even though the surface water largely disappeared, we're confident substantial water ice is still locked up in subsurface reservoirs. The radar data and ice stability models confirm that.
Which brings us inevitably to the ultimate question, the one that really grabs everyone.
Right.
Given everything we've learned, the past water, the changing climate, the current conditions, does it seem like life could exist on Mars today?
Ah, the big one. Well, the surface conditions today are incredibly harsh for life as we know it. We've talked about the low pressure liquid water just boils or freezes instantly.
Right.
Then there's the radiation. Without a thick atmosphere or a global magnetic field, cosmic rays and solar radiation bombard the surface, plus high levels of UV light. And the soil itself seems to be highly oxidizing, chemically reactive, which would break down organic molecules.
So finding organics on the surface is hard.
Very hard. The Viking landers in the 70s actually looked for organic molecules and found extremely low levels, possibly delivered by meteorites, suggesting anything native gets destroyed quickly on the surface.
Okay, so the surface is tough. What exactly did Viking do to look for life itself back then? What were those famous experiments?
Viking had 3 dedicated biology experiments, very ambitious for the time. The first was the gas exchange, or GX. It basically added a nutrient broth, sometimes with water vapor, to a soil sample and looked for changes in the gas composition above it, like oxygen release or CO2 consumption, signs of metabolism. It did see gas release, particularly oxygen when humidified, but scientists eventually concluded it was likely a purely chemical reaction with oxidants in the soil, not biological.
Okay, one down. What else?
The second was the pyrolytic release, or PR, experiment. This one provided Martian atmosphere with radioactive carbon dioxide, incubated the soil sample under a lamp simulating sunlight, then heated the soil to see if any of that radioactive carbon had been incorporated into organic matter by hypothetical microbes.
Like photosynthesis, kinda?
Sort of, looking for carbon fixation. The results were mostly negative or ambiguous. The third experiment, though, the labeled release, or LR, was the most controversial.
Why is that?
It added a drop of nutrient solution containing radioactive carbon compounds to the soil and monitored for the release of radioactive gas, which would indicate microbes were metabolizing the nutrients. And it did show a rapid, strong release of gas, initially looking very much like a positive biological signal.
So that sounds like life.
Well, that was the initial excitement. But subsequent analysis and experiments suggested that highly reactive, non-biological oxidants in the Martian soil could mimic that result by chemically breaking down the nutrients. So the official conclusion from the Viking science team was no unequivocal evidence for life. But the LR result, it's kept the debate going for decades.
No clear yes, but maybe not a definitive no either, especially from that LR experiment. And you mentioned the subsurface.
Exactly. While the surface seems hostile, conditions just meters below ground could be very different. Shielded from radiation, potentially warmer due to geothermal heat, maybe even hosting pockets of liquid water where ice melts near heat sources. That's where many scientists think the best chance for finding extant Martian life, if it exists, might be.
So the search continues, but obviously we have to be incredibly careful not to contaminate Mars with Earth life.
Oh, absolutely paramount. Planetary protection protocols are incredibly strict. Spacecraft going to Mars, especially landers, are rigorously sterilized. And scientists define special regions on Mars areas where Earth microbes might be able to survive and reproduce, or areas thought more likely to harbor Martian life, and there are extra precautions for exploring those zones.
Makes sense. You don't want to find life only to realize you brought it with you.
Precisely. And future missions are designed with this in mind. Things like the European ExoMars rover, which is designed to drill up to 2 meters down, and ongoing analysis by rovers like Curiosity and Perseverance, are focusing on looking for complex organic molecules, potential biosignatures, and exploring those ancient environments that might have once been habitable or maybe still are deep down.
It's incredible. Despite decades of robotic exploration and everything we've learned about its dramatic past, this journey from wet to acidic to dry and cold Mars still holds its most profound secret, doesn't it? The planet's history of water, those clues of its lost magnetic field, the strange chemistry, and those intriguing, ambiguous Viking results. They all point to Mars as maybe the best place in our whole solar system to try and understand the very definition of life beyond Earth. What will we find when we finally drill deep enough? Until next time we meet in another episode of Tiny Talks Big Ideas podcast, stay safe, stay healthy, and stay curious.